Okay, so let's go ahead and get started today. If you remember last time, we ended where we were talking about alcohol reactions, and we had gotten to the point where we were looking at not the C to O type of alcohol reaction, but the O to H. And the first example we looked at was taking an alcohol and reacting it with tosyl chloride in the presence of pyridine, and we saw that we obtained the tosylate, where we have substituted the tosyl group onto the oxygen of the alcohol. So the bond that is broken is the O to H bond. So this is a different type of reaction than we talked about in the last lecture. And I promised we would start at this point. Byproduct of this is HCl. And so mechanistically, what's happening here, it's worth looking at it just for a second. Drawn out like it is, I'm going to erase this part of it so we can just start here with the mechanism. And basically what's going to happen is this is your nucleophilic oxygen, and it's going to react with that sulfur, which we can imagine is the electrophilic center, because that sulfur is attached to a chlorine and two oxygens. Okay, and so when that new bond is formed, we can just, do a shorthand and say we're going to lose that chlorine as the leaving group. And so the result of that mechanistic step is this intermediate where we still have the H on our oxygen, and so that's going to have a plus charge. It is reacted with the sulfur, which has displaced the chlorine, which leaves this as our intermediate. And then it's simply a matter then, I lost chlorine here, so I have Cl minus, and it's simply going to remove this acidic proton, pushing the electrons back to the oxygen, and therefore I'm going to produce my product, which I'm going to abbreviate. Remember, at tosylate we did TOS in last semester. The abbreviation hasn't changed. Okay, but I'm also going to produce HCl. Okay, and now what's important here is we don't want any HCl sitting around at the end of this reaction, because that chlorine could come in and react with the electrophilic site of this tosylate and displace it, and you'd end up with the alkyl chloride. And so we need a way of getting rid of that HCl as it forms, and that's why the pyridine is present. Because remember the structure of pyridine? Pyridine is simply the benzene ring where you've substituted a nitrogen into one of the positions, and it's basically going to then react with HCl as it's formed. The nitrogen is going to take the acidic proton, and when it does that, it's going to form a salt. And here's what's important about that salt. We know something already, right, about solubilities. So we form this, what's called a pyridinium salt, and that is not soluble in the solvent in which the reaction is done. So this pyridinium salt just falls out of solution. And therefore you're really physically removing HCl from the reaction. So you don't have to worry about this nucleophilic chlorine being around to disrupt the reaction. Very common theme you see in organic when HCl is a byproduct of the reaction. If you see pyridine in there, pyridine is there to remove the HCl. So it is out of the equation in terms of reactivity. All right? And so now that we've seen this new reaction, you remember it's kind of in the same theme as we saw with CO alcohol type reactions in that this reaction that we just looked at, it makes OH a better leaving group. All right, so when we form this tosylate, we're doing that because we want to do further chemistry on it. We want to be able to react it with a specific nucleophile. But it brings up an important thing that we mentioned at the beginning, the difference between these two types of reactions. So remember I showed if you have your alcohol like this, and it's chiral, if you're doing a C to O type reaction, you're breaking a bond to this chiral carbon. So therefore your reaction can actually give different stereochemistries. But if the bond you're breaking in the course of your reaction is the O to H bond, it doesn't affect the chiral center at all. So these two types of reactions have a very different effect on stereochemistry. So that's what we want to look at right now, because it brings a synthetic strategy to mind that we need to look at. And that is when you're doing an O to H reaction, so I'm basically summarizing what I just said, you have retention of configuration if you have a chiral center. So nothing changes about the stereochemistry, because if you need to review those terms for stereochemistry, this would be a good time to do that. But when something is retained, you're not affecting the chiral center at all. But when you do a C to O reaction on a chiral alcohol, you're going to see either inversion or retention of configuration, which is basically going to depend on what kind of reaction you're doing. Okay, so basically it's possible to retain, but in the examples we looked at, you're most often going to see inversion. So how would this work into a reaction? Well, let's just say that the general reaction you want to do is take an alcohol and convert it to something where you've substituted a nucleophile into this. And let's just say that it happens to be chiral. Well, what are the ways that we've talked about doing this? The first is we said, when we talked about using these mineral acids like HCl or HBr, we were forming, the X group here, which was a leaving group. Okay, and remember when we did that, we were converting this into a better leaving group, okay, by protonating it and then reacting it with the X. If this were chiral, it's an SN2 reaction, right? So that's actually an inversion that's occurring. So that center would be inverted. And then if you came in with, some nucleophile and reacted then with this center, lose the leaving group, now you've done what? Another SN2-like reaction, so you've inverted again. Whoops. Let's continue our arrow up to there. You've done another inversion. So you've done basically a double inversion. Inversion. And so you've inverted the chiral center here, and then you've inverted it again. And so what does it mean when you do a double inversion? It's an overall retention, because you've inverted the center and then you've inverted it back. So overall, it's a retention. So if you did a synthesis with that strategy that we talked about with the CO type reaction, you're going to end up with overall retention. However, if you instead use the strategy where you convert this into a tosylate, now I have a chiral alcohol, and I'm going to treat it with tosyl chloride. And when I do that, I'm going to form this tosylate. But this step is retained. So it's retention of stereochemistry, because nothing has happened to the C to O bond. So whatever chirality was here is present here. Then, when you react this with the nucleophile, this is an inversion. And so now if you have a retention and then an inversion, the overall reaction is going to be inversion. Okay, so two different strategies, converting alcohol where I substitute a nucleophile in, and now I have two methods. One of them gives overall retention, one gives inversion. So how could I demonstrate that in a reaction? Well, it gives me what basically we always call complementary strategies. Just like a complementary reaction is a way of doing the same transformation but with different stereochemistries. Now we're going to see how a synthetic scheme can be the same way. So let's look at an example of this. Let's say that we have this alcohol. Okay, secondary alcohol. All right. And I'm going to first go through a method where I'm going to convert this to a good leaving group, okay? And then I'm going to react it with a nucleophile. And so let's do PBr3 instead of the mineral acid because this is a secondary alcohol, right? But it does the same thing. It's converted to a better leaving group, so when the bromine comes in, it inverts that center. Okay, and so if this started out being R, which I think if you play the home game, you can figure out that this is R, this chiral center. When I do my reaction, the bromine is going to come in from the opposite side of the leaving group, and therefore I'm going to put my methyl group there. I'm going to end up with the inverted center, so now that's S. Okay. And so bromine opposite stereochemistry as the leaving group was. Okay? Then I can take this alkyl halide and react it with whatever nucleophile I wanted to substitute in there. And I'm going to use ethoxide. Okay? And I do it in ethanol as my solvent. And the result of that then is this is also an SN2 reaction, right? And so that means that my OH is going to come, my OCH2CH3 is going to come in from the opposite side of the bromine. So it's going to come in from the back side. And so that means I'm going to return to the R configuration. Double inversion. So I've substituted my nucleophile for the alcohol going through a leaving group. But I've done it in a way that I get inversion, therefore overall retention. Okay? But what if I didn't want the retained product? What if I wanted my nucleophile to have the opposite stereochemistry? I'd have to change my strategy. And so to do that, starting with the same alcohol, secondary in the R configuration, now I can convert it to a better leaving group, but not using an SN2 type reaction. I'm going to use an O to H type reaction where I have used the tosyl chloride and pyridine. And so I end up doing what? I put the tosyl group on the OH, but it's in the same stereochemistry because I never broke the C to O bond. I broke the O to H bond to put the tosyl on there. So if this started out as R, this is still R. Retained stereochemistry. Now I can take that intermediate and react it with the same nucleophile I did before, ethoxide, ethanol as the solvent. Okay, so my nucleophile is going to react with that center, but it's going to do it in an SN2-like manner. So then my nucleophile ends up on the opposite side of the leaving group. So I have now inverted the configuration, and this is now S. Okay, so here I did a retention, inversion, so I got overall inversion. Okay, so do you see how using two methods, I did basically the same transformation. I substituted this OCH2CH3 onto this molecule where the OH was, but I could do it two different ways. I could either get it where it gave me the R retained product or the inverted S. So synthetically very important things to remember. Okay? Now, next topic, that's really all of the reactions that would qualify as the two types. And since we talked a little bit about synthesis right there, we want to talk about something else with OH groups, because alcohols are very common intermediates in synthetic steps, and sometimes, as we've seen, they can also interfere with the synthesis. Remember when we talked about Grignards, we said that Grignards, one limitation was if there was a acidic proton present somewhere on the molecule and you couldn't transform it to the Grignard and do a reaction. And one of the cases was if there was an alcohol present. Okay, so what we want to talk about is a strategy called protecting groups. And that is if you're doing a synthesis and you get to a point where you want to do a certain transformation, but you have an interfering group, there's a strategy where you can react something with that group and basically, mask it so it's no longer reactive. You can carry out the chemistry you want, and then you just remove it. So you're protecting that functionality from the reaction. So it's a protecting group. Okay, and so how do we use protecting groups in synthesis? And we'll talk about a couple of examples of this as we work through the rest of the semester. But the protecting group we're going to talk about right now is specific to alcohols. Okay, so when would we run into a situation like this? And I already mentioned the Grignards, when we're using them, we can't have acidic protons. And so therefore, let's just say that we had a molecule that I'm just going to draw as this little hot dog. So let's say you have a molecule. And on one side of the molecule, you have your X. And so I want to produce a Grignard from this alkyl halide, remember, by reacting with magnesium. But the problem is, I also, on the same molecule, have an OH. And that OH interferes with the reaction. So what can I do to handle that? I need to be able to allow this reaction to occur. Because if I try to treat this with magnesium to form the Grignard, it's not going to work because of the presence of this OH. Okay? And so what do I need to do? I need to somehow protect this OH where it no longer interferes. Okay? And so here's the strategy that we use. Okay? So now this is just general strategy. So the first thing we want to do, and we'll talk about this in steps, and we'll work through this logically because I think that's the best way to do it. So the first thing you want to do if you're wanting to protect a functionality is you need to have something that will react with the alcohol and not anything else on the molecule. So introduce a protecting group to the interfering functional group. And in this case, it's the alcohol, forming, well, what would be the best kind of protecting group? Something that would react with the alcohol, therefore masking it, but then also once that forms, you want it to be inert to the reaction you're going to perform. So in other words, you want that protecting group to go on the alcohol and then just sit there while you're doing whatever chemistry you want to do. And then you can come back later and take it off, right? So the interfering functional group forming an inert derivative. Okay? And then once you have that on there, of course, then you carry out your reaction. Whatever that reaction is on the rest of the molecule. In the example we're looking at, it's a Grignard, but whatever the reaction is, you want to be able to carry that out. Okay? And then once you've carried out the desired reaction, The last step would be to be able to remove the protecting group. Okay? And so when you're looking at that, you kind of, and we'll talk about this in more detail in a minute, but if you look at those three things, protecting group chemistry is very important, and it's kind of difficult because what you're asking for is something that's easily put onto the molecule to protect it, but you don't want it to be reactive to many things so you can carry out reactions, but then you want it to be easily removed. And so it's almost, the 2 and 3 steps are almost contradicting. You don't want it to be very reactive. You want it to be inert, but you want to be able to remove it easily. And so picking protecting groups is very, very important. And the one that we're going to talk about as our example, again, is one that's commonly used with alcohols. And so the example that we'll look at is the formation of TMS ethers. Okay, TMS is trimethylsilane, so TMS ethers. Okay, and the way to make them is to take your alcohol functionality and you're going to react it with this trimethylsilane, where you have 3 methyl groups and a chlorine. Okay, and then I'm going to treat this together with something added to the reaction called T, believe it or not, which is triethyl amine. And triethylamine, we're going to see, serves exactly the same purpose that pyridine did, because I'm going to form HCl in this reaction. Okay? And so basically what's going to happen? Well, we know by now we have an alcohol in the presence of this electrophilic species. The O is going to form a bond with the silicon, which is going to kick off the chlorine, right? And so allow me to, because I know that you can pause and look at this, I'm going to erase this so we can draw then the result of that. Mechanistically, we didn't lose our H, so we still have a plus. We reacted with that silicon center. We have our 3 methyl groups there, right? And then we have formed Cl minus, right? And then Cl minus can pull this proton off, so these electrons come back in. And you form, as a result of that, what we abbreviate as the TMS ether, which is basically where we have the silicon with 3 methyl groups. So this really is a O to H type bond for the alcohol, which is important to know if you're looking at how it affects stereochemistry. But believe it or not, it's an SN2 reaction. And who initially has a problem with that? Notice that the nucleophile was reacting into, if you look at the silicon, it had 3 methyl groups on it and the chlorine. So it is in essence a tertiary system. We said tertiary systems don't undergo SN2. This one does. You know why? Because the silicon to carbon bonds are much longer than a carbon to carbon bond. Therefore, there's not as much steric hindrance. And so actually this tertiary system can undergo an SN2 reaction. And this might be an interesting short answer question on an exam. All right, and so once this forms, remember, I have now produced HCl. But HCl causes a problem because it can react and remove my TMS group. And so as this HCl is forming, I need it to be removed from the reaction. And remember, we have this triethylamine that's in the reaction mixture, just like the pyridine did. The nitrogen pulls off this hydrogen and it forms the salt. It would look like this. And again, that's not soluble in the normal solvents that you do the reaction in. So that precipitates out of solution. So you're removing the HCl from the reaction. Okay? So pyridine and triethylamine kind of serve that same. They're actually called proton sponges because they basically just remove HCl. All right? So this is how I could form a TMS ether. And it's a good protecting group for alcohols. Because remember, to just emphasize this, in order for something to be a good protecting group, we need the following to be true. We need it to be unreactive. So once it's introduced onto the molecule, we need it to be inert to as many things as possible. But we also need it to be easy to remove. And that is kind of the contradiction that seems to exist. Okay? But the great thing about TMS ethers is they qualify as a good protecting group because they are unreactive towards oxidizing agents. So, PCC and potassium permanganate, so you put this protecting group on. If you put an oxidizing agent in it, the alcohol will not be oxidized. Reducing agents and Grignards. Okay, and so in our particular example, that's what we're concerned about. Inert to Grignards. Therefore, they remove the issue of having an alcohol present. Okay, so the nice thing then too is the second part, TMS ethers are easily removed. Okay, by acid. And I'm going to say it's really more commonly aqueous acid, unless you're using something. You can also remove it with anything that's got a fluoride anion. Will easily remove it. Okay, and so that means, just for example, if I had a TMS group, and I'm going to use the abbreviation, if I had a TMS ether where I've protected what was the alcohol, all I have to do is treat this with an aqueous acid, and I will obtain back the alcohol. So what that means is easily removed with acid, but that also means that it is not inert to acid. So it's not a good protecting group if you're going to be using something acidic. And that's why when we produce it with TMS chloride, we have to use T to remove the HCl. Otherwise, the TMS ether will just come right back off as the HCl is formed. Okay? All right, so let's work through an example so you can kind of see. I know going through this in a general sense is often hard to see exactly, how are we actually going to use that in a synthesis. So let's look at this example. Let's say that we have this compound, which is a halohydrin, because it has a Br on one end and an OH on the other. Okay, and let's say that we want to use this as a Grignard reagent, so I want to convert this into a Grignard. But the problem is there's an OH on there. Okay, and so what am I going to do? Here's the strategy. Let's say protecting group strategy. And so the first thing I'm going to do is protect the alcohol. And so to do that, I'm going to take my halohydrin and I'm going to react it with TMS chloride. in pyridine. Okay, and so that's going to then do the CH type reaction on the alcohol, and I'm going to form the TMS ether. Then I am free to make the Grignard. Okay, and to do that, I'm going to take and I'm going to kind of invert the molecule just to make it easier to look at here. So I have my TMS ether and my halide. And to make the Grignard, remember, all I do is magnesium metal and ether. And that's going to form the Grignard. And it can do that because the alcohol functionality is masked. So I'm able to form that Grignard. Okay? Once that Grignard is formed, then I can carry out my reaction. Now again, I know that you're able to pause and rewind and all that, so that's why I'm erasing so quickly. And so step 3 would be carry out the reaction. And to do that, I'm going to take my Grignard, and I can do any reaction which a Grignard undergoes. And so just for fun, let's have it react with an alcohol. I'm sorry, an aldehyde. An aldehyde. And remember, it's always followed up with an aqueous acid workup. And so what does this do? Remember, in a Grignard, this is the nucleophile. It reacts with that electrophilic carbon of the carbonyl. It's a reaction we talked about already. And it gives the addition product, so we're going to end up with an alcohol product, right? And so the product that forms, I have this TMS ether, and I have this carbon then was adding to the carbonyl carbon of the aldehyde. It's an addition, so you end up with this secondary alcohol. Okay? Now, then all you would have to do is remove the protecting group. And you would do that by taking that structure above the TMS ether and react it with aqueous acid. And it would give me the product where you would get back your alcohol functionality, and then you would have your alcohol functionality that you formed in the reaction. Now, does anybody see anything interesting about this? In the second step of this reaction of the Grignard with the aldehyde, I did an aqueous acid workup. And so this final step may not even be necessary, because when you do the aqueous acid workup of the Grignard reaction, it's probably going to remove the TMS in the same step. But the reason I put it in here is maybe it doesn't completely, or it's not always the fact that you do a reaction that has an aqueous acid workup that just in tandem would remove this. So you have to remember that if it's not removed in the course of the reaction, you need to remove it in your final step. So that's how protecting groups are used, where you can do a reaction like this. So if you're ever doing a synthesis and you need a hydroxy group in your product and you want to use a Grignard reaction, you know how you can do it with protection. All right? So that's kind of everything we need to talk about with alcohols, okay? And one thing that I've been thinking about is exactly where the material needs to stop for the test that the window is going to open on April 15th, okay? And I think that we have reached that point. And so this test that you're going to take between the 15th and the 19th is going to cover through alcohols. Okay, um, it's a little more material than is normally on that second test this semester, but we're giving more time for you to work on it because there'll be several other lectures um, that come that won't be material that's on the test. Okay, because I think this lecture is actually the April 10th lecture, so I mean you're having almost a week ahead of time, or 2 weeks if you don't start taking the test until Friday or Saturday of that window. All right. So the next thing we're going to start talking about is thiols. Thiols are basically the sulfur analog of alcohols. And because of that, their reactivity is kind of similar, and so is their nomenclature. We're going to start with nomenclature first. Okay, and nomenclature, you're using the same rules as you did for alcohol. So all you really have to do is look back at the rules for alcohols. Everything is the same except your suffix changes. The suffix now is thiol, which makes it really easy, right? And so, for example, if you're going to name a thiol, all you do, remember, is you're going to name the alkyl portion and then add the suffix thiol. So this would be propane, and normally, remember, we would drop the E and add OL, but our suffix starts with the T. And so what did we always do in that case? We left the E. So all thiols, you actually leave the E for the alkyl group. So it becomes propane thiol. Okay? How about this example? Cyclohexane. And again, you don't have to drop the E because you're going to be adding a T of the thiol. So cyclohexane thiol. Another example. Okay, here, if this were an alcohol, remember you'd be numbering from this end, 1, 2, 3, 4, right? Where I have my group, so this would be 2-butane, leave the E because you're adding a suffix with T, 2-butane thiol. Okay, so very easy nomenclature, just follow the rules for alcohols and just remember that you leave the E when you're adding the suffix because it starts with a T. Now the only thing that's left then is what about if it's a substituent? So let's say you're naming your compound and you have SH as a substituent. The substituent name for a thiol makes no logical sense. Okay, the substituent name for this is mercapto. And so when you're looking at this, if you're naming it as a benzoic acid, it would be 3-mercapto benzoic acid. And you might be saying, how on earth do we get the name mercapto? There's actually logic to it. So here's the way you remember it. Okay, it's mercapto because thiol compounds are used if you have mercury poisoning. The drugs that they give you to remove the mercury are thiols because thiols interact with mercury very readily. So they capture the mercury in a system. Thiols capture the mercury, so they're mercapto is where that name came from. Okay? Now, what are the physical characteristics of thiols? Well, the biggest one is stench. They smell really bad because examples of where you find thiol compounds are skunk scent and natural gas additives. They add about a part per billion of a mercaptan in natural gas because natural gas has no scent. So they add that part per billion of thiol into the natural gas. So if there's a leak, you're actually able to smell it and determine that there's a leak. And so if you know that pungent smell of the natural gas additive, and of course, if you've ever smelled a skunk, the thiols stink. And I've got two stories related to that. And I can't remember whether I've told this story, but the Darth Vader story. When I was at Cornell, I was working on a reaction where I was using thiols, and I was doing the reaction, and it was early evening, and I'm sitting there in the hood working. Um, you know, I'm in the hood, but I'm working on the reaction with the thiol, and all of a sudden I hear this, this weird breathing sound, and I turn around and it's a fireman that's totally in the whole breathing apparatus thing, pointing at me to get out because they thought there was a gas leak. I evacuated 3 buildings on the Cornell campus and because they thought that there was this major gas leak. So I kind of got in trouble and was told I can only work up that reaction after midnight from then on. But so it doesn't take very much for an incredible scent to get out. But another thing that's kind of an interesting aside is when there's a natural gas pipeline and they're testing it for leaks, they basically, believe it or not, can just fly now, I guess, drones. In the old days, helicopters or whatever, they would just fly along the pipeline and they'd look for buzzards circling. Because if there was a leak of the natural gas, it would attract buzzards because that's the same gas given, their thiols given off when the bacteria is digesting a dead carcass. So these circling buzzards indicate that there's a gas leak. It's kind of interesting using a natural phenomenon to determine leaks. But anyway, so it stinks, okay? And so before we talk about reactions of thiols, the first thing that we always do is talk about how to prepare them. And there basically is one good way of preparing thiols, but there are two that you could imagine. And so we'll call this preparation. So how can I prepare a thiol before I do a reaction on it? Okay? The easiest way that you might imagine is to take an alkyl halide, and because all of us kind of think SN2 type reactions now, and you would just have to react it with the sulfur equivalent of sodium hydroxide. Is then I'm going to have this thiol nucleophile, which could come in and react with the electrophilic carbon of my alkyl halide and push these electrons out to the bromine. And when I do that, I would form the substitution product where my thiol will have substituted for the bromine, and I would get sodium bromide as my byproduct. Well, you would think that that reaction would work really well, but there's a problem. Sulfur is very nucleophilic. So this could come back and react with another molecule of starting material. And if it did that, you would end up forming the sulfide. And that happens enough where it actually makes this reaction kind of low yielding, because you don't want that to happen if you're forming a thiol. Okay? And so this reaction doesn't work very well, but there is a better one. and it's an improved synthesis, and it uses thiourea. And way back at the very beginning of organic chemistry, we talked about urea, so you'll recognize what thiourea is. So using the same alkyl halide that we did before, now instead of using the thiol analog of sodium hydroxide, I'm going to use this thiourea, which has this structure. We know this is an electrophile, and so this has to be the thing that's nucleophilic. Remember, we just said that sulfur is really nucleophilic. So in this case, it's going to come in and react with this electrophilic carbon, displacing the bromine. And so what's going to form is this intermediate. So when I formed a new bond between this sulfur and this carbon, okay, it's going to get a plus charge. But the counter ion is the bromine that comes out. So I formed this salt. And this intermediate is actually reasonably stable. I mean, it'll stay in the reaction mixture. Okay? And why is that important? Because when the sulfur does that initial addition, you form something that's stable. So you can react all of your thiourea with your alkyl halide without any chance of this sulfur being nucleophilic enough to react again, because it's actually got a plus charge here. That sulfur is not nucleophilic anymore. Okay, so I formed this nice stable intermediate. Once all of my thiourea has reacted with the alkyl halide, then all I have to do is treat this with sodium hydroxide, and I will remove everything to yield the thiol. Okay? Now, one thing you might want to think about at the home game, and I want you to think about this, and maybe in one of our 11 o'clock meetings we can go over this, but mechanistically, I'll give you a hint, but it's kind of a fun one to work through on your own. This is removed when my OH reacts with the electrophilic carbon that's in this intermediate, right? Because it's next to two nitrogens and a sulfur, which is now even more electronegative because it has a plus charge on it. And so work through how you think this is removed, and I'll give you another hint. The byproduct is just plain old urea. So how does that mechanism work? Something for you to think about on your own. Okay? And so that's one way of making a thiol. Another one is through oxidation and reduction. And that is if you have, and I should really, this is really kind of, it's not as much preparation as it is, and we'd almost want to say that it can fall under reactions also, because it is a way of, it's a way for thiols to go back and forth between one thing or another. If you have two thiols, you can oxidize them with bromine, and you will form a disulfide plus HBr, and to balance, that's a 2. Okay, so you're forming a disulfide. But you can also take the disulfide, treating it under reducing conditions, zinc and acid, and you actually can reform the thiol. And this is a reaction, you biologists know this, or anybody that's taking biochemistry. This is, a disulfide is what? It's a disulfide bridge. This happens in proteins when you get cross-linking, where you have the thiol functionality on your amino acid, and we all know which one that is. You can get this bridging when you oxidize, and then you can also then return to the thiol. And you've probably seen the experiments in biochem where you're doing sequencing of proteins and you always have to break the disulfide bridges first. You're using this kind of chemistry to do that. Okay, but it's also the chemistry that's used for doing hair permanence. Believe it or not, a little extra aside, because your hair has tertiary structure, right? There are disulfide bridges within the proteins in your hair if you had enough hair. And you can, when you get a permanent done, basically what they do is they break the disulfide bridges and then you reform the hair in whatever position you want it to stay in, and you reform different, or so I should say you form different disulfide bridges so the hair then retains that shape. But of course, everything returns to what is more stable. So over time, your hair, the protein in the hair the disulfide bridges will break and reform to their original structure. So kind of an interesting aside there. All right. And so that's bringing us to our discussion now of, again, things related to alcohols and thiols. It brings us to ethers. And so we're going to talk briefly about ethers and also a special kind of ether, epoxide. And why would epoxides, even though they're ethers, why would they have a special little section of the next lecture? Because their reactivity is a little different than ethers. They are an ether, but remember, an epoxide is this three-membered ring. You have the ether linkage in here, but these are more reactive than ethers because they're in a constrained three-membered ring. Okay? And so just kind of as a start, a transition for the next lecture, ethers, that's a functionality that we learned early on. And ethers are basically what? How would you define them? They're a substance with two organic residues attached or bonded to the same oxygen atom. And so R to an O to another organic residue. So what's important is that these are R groups. Okay, so there's a carbon on each side. And the R group can be alkyl, aryl, remember aryls are like benzene rings, vinyl, so that means that there can be an sp2 hybridized carbon, cyclic, or acyclic. So there's some flexibility on what the organic residue is. Okay? So the next thing we will talk about, new functionality. So we're going to talk about nomenclature of ethers. And that'll be where we pick up next time. This is a good stopping place. We've gone about 55 minutes. I know that's not as long as we normally do in the lecture, but this is a good stopping point. And so I will see all of you in one of the 11 o'clock meetings.